Welcome to this laboratory for the course Sustainable Energy Management and Efficiency for Data Centers. In this practical session, we put into practice many of the concepts covered earlier in the course. The goal is to show how Python can be used to simulate, analyze, and optimize the energy consumption of a data center. We work with a synthetic dataset that mimics real monitoring data, compute efficiency metrics, detect anomalies on the IT load itself, and test our what-if scenarios by adjusting cooling strategies. The lesson is structured around 5 main steps, each corresponding to a section of the code. To make this hands-on lab session accessible to everyone, we will use a Google Colab, a free cloud-based environment for running Python code. Colab provides a Jupyter Notebook interface directly in your web browser without requiring any local installation. So we begin this script by running the cell. This cell regards the main imports of the library for the script. So we move to the first step of this hands-on lab, in which we want to create a synthetic dataset that covers a full year. So we have to generate 8,760 hours of observation. So here we simulate different variables, including ambient temperature, the IT with weekly patterns, UPS losses, and cooling system performance and carbon intensity factor. We can compute the ambient temperature as a combination of a daily component, which represents daily fluctuation of the temperatures, and a seasonal, in this case annual fluctuations. So we combine these terms, adding baseline temperatures to compute the final ambient temperatures that will feed our synthetic dataset. The next variable that we want to simulate is the IT load. So in this case, we suppose a baseline of 400 kilowatt, and to this we add some random noise, but we want to keep it constant to simulate that the workload of the IT servers is as most constant throughout the years. Finally, these values are then clipped in order to avoid extreme values, so they are clipped between 250 and 600 kilowatts. Finally, we simulate the UPS losses. So they are calculated starting from the IT load, and we suppose 2% of the IT load kilowatts. Also, UPS losses are clipped, so we avoid the numbers be less than zeros. Finally, we simulate the cooling demand, which is driven by a set point, in this case of 22 degrees. The COP degrades slightly as ambient temperatures rises above the set point. This cooling electrical load is computed as a thermal load divided by COP. Finally, all these signals are assembled into a data frame, which is a structure for data of the library pandas, which can help us to manage and process this data more easily. In the next cell, so we can plot the daily average load profile in order to see the long-term seasonal patterns and weekly trends in data centers load. We run the code. In the plot, we see a baseline of around 485 kilowatt, whose main contributor is, of course, the IT load. And then we see main seasonal patterns, which are due to the cooling system, electricity demand, which is driven, of course, by the ambient temperature. The step 2 of this hands-on lab session will be devoted to calculate the key metrics for computing data center efficiency. So we will evaluate facility energy consumption, PUE, power usage effectiveness, the CUE, and the COP. We will compute these formulas starting from the data frame. So the total facility electricity consumption is given by the sum of demand of the components we have simulated before. Then we compute the PUE given by the ratio between the facility consumption over the IT load. To compute the CUE, we first compute the amount of emissions starting from the total facility consumption and dividing them for the IT load. In order to have insights on the average performance of the data center, we compute the average values of these metrics. So we compute the average PUE, the average CUE, and COP. These are the results. So we see that the PUE is around 1.2, which is a really good value. So a PUE of 1.2, 1.5 suggests that the data center is quite efficient, while values near 2 indicate more opportunity to improve. So in this case, the data center is already efficient, but there are still some improvements that can be done, especially in decarbonizing supply and optimizing cooling. Then we can also visualize some information over time. For example, we can plot the PUE time series over time. Here we can understand how the efficiency fluctuates with operating conditions. In our case, the PUE sits around 1.2, but it varies, reaching values of 1.25 during summer periods. In particular, this low rise in the PUE and fall are the effect of seasonal cooling effect. In short, higher ambient temperature means more cooling, and more cooling means higher PUE. In the next cell, we can also show the average power breakdown. By running the code, we see that the main component for the data center consumption is given by a IT load. Of course, we simulated it to be around 400 kilowatts, and it accounts for about the 82% of the total facility consumption. As we know, the second major component of the total consumption of the facilities is given by the cooling system, which accounts for around the 16% of the total load. And finally, we have the UPS system, which consumes about the 2% of the total load. In this last plot, by running the cell, we also plot the COP over time to highlight how cooling efficiency moves with the weather. And COP typically falls during a warmer period, since it is highest in winter and it slows down in the summer. In particular, as we can see, the COP mirrors the PUE. And of course, when it's warmer, the system needs more electrical power per unit of heat removed. And this pushes the PUE up and the COP degrades as a consequence. The next step of this hands-on lab session will instead deal with anomaly detection. So in this case, we want to simulate some anomalies in the IT load. So we simulate them in an artificial way. So we inject two types of anomalies into the IT load. A first sustained drift for a longer period of overconsumption, and a sudden spike. So we have in this case a short pulse of unusual high load. And then we test two strategies, one algorithm of machine learning, the isolation forest, and then the Z-score fallback, which is a more rule-based strategy, in order to understand if these anomalies are detected. So we create a new vector, the IT load anomaly, and we suppose that we have a raise of 20% for 200 hours and a spike of 200 kilowatts for 50 hours. By running the plot, we can see in blue the original IT load, which is quite constant over time, and then we can see the anomalies. So we have the anomaly for the longer period, shorter in amplitude, and then we can see the spike of 200 kilowatts. So we've run the anomaly detection using the isolation forest, and as we can see, this algorithm is able to identify these anomalies, and this can be useful to detect inefficiencies in the system. The last and final step of this hands-on lab session instead we deal with a what-if scenario simulation. So we want to understand which is the impact of raising the cooling set point from, in this case, 26 degrees. Then we will calculate the new PUE, and we will try to understand which are the energy savings in this case. So in the code, similar to what we have done before, we define the new set point to 26 degrees and calculate the metrics for this new configuration. So in this plot, we can compare the PUE in the current case with the PUE with this new case with a higher set point. And as we can see, with a higher set point, there is a lower cooling demand. Therefore, the PUE is lower than the base case, since it is less dependent on the ambient temperature. Finally, also for this case, we can recompute those metrics we have calculated before. So we can evaluate the average PUE, average CUE, and COP. So we finally calculate, as we have done before, the average metrics of PUE, CUE, and COP for this new configuration. So we run the cell, and we also compare these results with the previous case. In terms of PUE, there's a slight decrease as well as the CUE, while we have an increase of the COP, since the cooling system in this case is more efficient since we have raised the set point. As a final consideration, we can also evaluate the total energy savings and analyze them. In this case, by raising the set point, we are able to achieve annualized energy savings of about 19 megawatt-hours. Synthetic data is useful for training and experimentation. Even if real datasets are not available, models can be tested on realistic simulations. Metrics like PUE and CUE are indispensable, but they need context. A PUE of 1.4 is good, but if cooling COP is low, there may still be inefficiencies. Machine learning enhances monitoring. Anomaly detection goes beyond human oversight and can prevent costly failures. Scenario analysis bridges monitoring and strategy. By testing alternative configurations, operators can make informed decisions without physical trials. Ultimately, this lab shows how digital tools transform raw energy data into actionable insights. With relatively little code, we can monitor efficiency, detect risks, and explore future improvements, all key to building sustainable and resilient data centers.